Now let's backtrack a little bit to Gauss's law. What is Gauss's law for? In the short answer, it's to find electric field strength. And I want to emphasize the word strength, and notice the E over here and E vector. What's the difference? Gauss's law finds E, it doesn't find E vector, okay? E is the magnitude of the electric field vector. It's just a lazy way of writing that. So make sure, remember, your answer should always be positive if you find electric field strength. The electric field strength is the magnitude of a vector, which is the length of an arrow. If you have the length of an arrow, a length cannot be negative, right? At most you have zero length, which means it doesn't exist, but you cannot have negative. So if you get a negative answer for just capital E with no vector, E, you know you're doing something wrong. Please check that, right? So let's see a quick example. Let's say I have a point charge over here that is positive Q, and then two thin shells like this. Let's say I have two thin metal shells surrounding it, with this one is minus 2Q and this is positive 3Q, something like this, okay? And let's say I'm interested in the electric field somewhere in between here. There's a three-step procedure you do to use Gauss's law, okay? The first step is you draw all the electric field lines. If you follow these three steps, that's always how Gauss's law would work to enable you to find the electric field at any point that you're interested in, for example, the X that I marked. You also need to decide the direction. Remember, the field lines is the direction. You think of a positive test charge and ask yourself which way will it go. So here it will go this way. A positive test charge will get repelled from the center, attracted to the -2. How about the next region? The next region, a positive charge would go this way, right? So this is the way the arrows would go. And how about outside? A positive charge will get repelled outside. So these are the directions of the electric field lines. Okay, so that's step number one. Step number two, write down Gauss's law, have this memorized. At first it looks daunting, but it's not that much. It's just these three. On the left is EDA, on the right is Q enclosed. I highly encourage you to write down what you're integrating over. You can look at my other videos, talk about, in this example it's not as important, but other examples is very important to write down the S. So if you're finding the electric field here, if you're interested in the electric field here, draw a Gaussian surface that intersects the electric field lines and intersect the point of interest. Let's say you're interested in finding the radius R, the electric field at radius R over here. Okay, so now the third step is you can attack the right-hand side and the left-hand side separately. Okay, so the right-hand side is easiest. So let's look at the right-hand side first. Everyone can do the first step. You just copy out this after you memorize it. Now you look at what is the charge enclosed in S. So this is your Gaussian surface that you're considering. What is the charge enclosed inside S? Well, it's Q and then minus Q. All these are enclosed inside S. So the answer is this, right? Inside S, so you have something like this. All right, how about the left-hand side? Now you can focus your attention to the left-hand side. And first step, you copy everything out, write down with what you're integrating over. The textbook doesn't have the S, which is a very bad habit. Anyone who write down integrals should write down the S, what you're integrating over with it. So first, there's an area and there's an electric field. What area? What electric field? On S, okay? So the area vector of S, we need to zoom in. On S, we need to find a little piece of area. Remember, it's a sphere, right? But dA means I want to look at a little piece of area over here on the S. And the area vector is defined as always a perpendicular vector away from the center of from the interior of the surface. That's how you define area vectors. It's a perpendicular from the surface and pointing out away from the interior. Okay, so that's dA. How about E? E is the electric field. Electric field where? Electric field on S, right? So what's the electric field on S? Just look at the blue lines. It's pointing this way on S. All right, so now you just need to do E dot dA. Now you need to remember dot products. How do dot products work? There's three answers. It can either be AB if they are parallel. It can be minus AB if they're anti-parallel. Or they can be 0 if they are perpendicular, right? The general formula is AB cosine theta. Theta is the included angle. So if they're 90 degrees, it's 0. Cosine 90 degrees. If there's 180 degrees, it's minus 1. So in this case, E dot dA, which case is it? Minus EDA. Okay. Once you have that, can you pull out? Is E a constant? No, E is not a constant, because the further away you go from the sphere, the E is going to be very weak. But if you go close to the center, the electric field is going to be strong. However, on S, it is a constant because there's no reason that E is stronger on one side than the other due to the symmetry. So E is as far as S is concerned, E is a constant. So a lot of people tell me E is a constant. It's not true. It's constant on S. That's why you can pull it out of the integral of S. And then now you just need to integrate dA. Let's integrate dA. What's A? A of what? It's good that we labeled S over here. It's A of the surface, S. And this is a sphere, right? So the sphere is 4 pi r squared. Especially my radius is r, so it's 4 pi r squared. Now you just have to match your left-hand side to the right-hand side to find E, right? Your goal is to find the electric field strength, and there you go. You see the minus signs cancel out, so E is Q over 4 pi r squared epsilon naught, something like that. Notice that it's positive, even though there's a negative sign and a positive sign over here, even though this is negative, as it should be, because electric field strength is always positive. All right,